So, hello to everyone who's watching on YouTube. Since no one has joined the session in person yet, uh, maybe we'll start in 10 minutes, just waiting for a few people to join the session in person. If no one joins, then maybe we'll just get started anyway. So I'll mute myself till then. So hi Mridula, we are just going to start the session in like 4 5 minutes. Just waiting for a few people to join the session in person. If no one else joins, then we'll just get started nonetheless. Till then, I'll just put myself on mute. Okay, so since no one has joined the session in person yet, maybe we can just get started nonetheless. So hello everyone. Just to reintroduce myself, I'm Lakshya Salki, the NPTEL Problem Solving TA for the Tuesday 6 to 8 p.m. sessions for the selected topics in algorithms course. And I believe this is going to be our sixth session. And in this session, we'll be moving ahead. So till previous week, we were discussing about randomized algorithms and like Markov chains and everything. And now we'll move on to a new set of topic, which is essentially complexity theory. So we'll be discussing the notions of NP hardness. What do we mean by when we say that a problem is hard? What do we mean by when a problem is like tractable and so on? So yeah, and again, like all the weeks, I'll be assuming that you guys have gone through this week's lecture videos before uh, coming to this session. So yeah, so maybe I'll just share my screen and we can get started. So I'll just share my screen in a minute. Yeah, so I hope my screen is visible to everyone. Uh, just maybe zoom in a bit that everyone can do it better. So yeah. So I believe this is going to be a fairly straightforward session. If you guys are somewhat familiar with these concepts, but if you're not, then yeah, uh, hopefully this session will help you understand or grasp the idea of what do we mean by NP complexity classes and what do we mean by when a problem is NP hard, when a problem is co-NP hard, and so on. So yeah, so so first of all, so this week, what we started was with this NP complexity class. So what is NP complexity class? So first of all, what's the motivation behind studying this complexity theory? So there are like many problems in which many practical problems as well as many theoretical problems for which we do not know any polynomial time algorithm even after many decades of efforts. So one might wonder. Suppose someone gives you a problem, and then one person might ask you, "Oh, give me an efficient algorithm for this problem." Well, it might be the case that even after trying it for a long time, you are not able to come up with uh, any efficient algorithm for the problem. Well, then maybe what's another way out? Well, maybe then you can try to, instead of trying to solve the problem, you can try to somehow prove that, yeah, this problem is hard or this problem is not easy to solve. And since these hard and easy are kind of very subjective terms, so we have a very formal kind of a definition for this. So, and what do we mean in computational complexity on complexity theory when we mean by classifying a problem as hard? So hard means that it's hard to admit a polynomial time algorithm for the problem. And why is it hard? Like it's not like proven that there cannot exist any problem, a polynomial time algorithm, but instead it's because well, people have been trying it for a long time and people have not been able to come with a polynomial time solution. So yeah. So and yeah, so the motivation behind this is classifying whether a problem can be uh, stated as hard or it can be solved in polynomial time. And can we compare relative hardness of various problems? So to say these kinds of things, uh, yeah, to classify whether one problem is easier or one problem is harder than the other, so can we have a framework uh, in which we can formally without any subjectivity, with actual mathematical, like with proper mathematical work behind it, can we formally say that some problem is as hard as problem two, like problem one is as hard as problem two. So, for example, for example, let's consider the decision problem. So, decision problem is a problem where the output is a Boolean, which is a yes or no. Like, so we'll be dealing with decision problems throughout. Uh, throughout this video. So we'll be assuming that the problems at hand are decision problems where the answers are just for any problem the answers are just yes or no. Either yeah. So there are two outputs and you have to output whether the answer is yes or no. So for example, what's an example of a decision problem? Suppose you're given a Boolean formula, an input, and then you're asked. So you're given a Boolean formula as input, and then you're asked, is there any satisfying assignment to this Boolean formula? So is there any assignment of variables to this Boolean formula such that when this Boolean formula is evaluated on that assignment, the output comes out to be true? And this problem is also called satisfiability problem. And yeah, this is kind of a very important problem in theoretical computer science, which will be coming on later. And maybe another problem can be given a graph G and integer k, and two vertices x and y as input. Is there a path from x to y containing at least k edges? So the problem asks us if in the graph G, uh, is there a path from x to y containing at least k edges, and k is part of the input. And this problem is called longest path. And why is it called longest path problem? Because essentially, even though this is a decision problem where the input is an integer k, but the output which you have to give is whether there exists a path uh, which has length more than k. And so if you have to find the length of actually the longest path in the graph, what you can do is you can just check, okay, whether the longest path has length k or not, has length k plus 1 or not, length k plus 2 or not, and so on. So that's why this kind of a problem also can give us the longest path from x to y in the graph. That's why it's also called the longest path problem. And the decision variant is this, that given a graph G integer k and two vertices in their path from x to y containing at least k edges. And yeah, so this is one example. And now coming to some like very important complexity classes. So some of the most important complexity classes are these classes. So of course the one class is the class P, which is the set of decision problems which admit a polynomial time algorithm, which is what we are always after. We want every problem to have a uh, polynomial time algorithm because uh, for our purposes like even though one can also go into this that in polynomial time we want to have a faster polynomial time, like instead of an n cube algorithm we want an n square algorithm or something like that. But even before that we would first like to not have a like exponential time algorithm. We would first want to have a like polynomial time algorithm first. And turns out even finding a polynomial time algorithm is hard for a lot of problems. And similarly, uh, the second complexity class, which is which is one of the most important classes, is the class NP. And NP is the class which contains a set of decision problems where for every yes instance there exists a polynomial size proof which can be verified by a polynomial time algorithm. Uh, Maybe I'll just mute myself for a second, guys. Yeah. So. So the problem class NP is a set of decision problems where for every yes instance there exists a polynomial size proof which can be verified by polynomial time algorithm. So essentially it means that okay, even if you are given the problem, it might be the case that you are not able to actually uh, solve the solve the decision problem itself and say whether the output is yes or no to the decision problem. But what you can actually have is that if someone gives you the solution that this decision problem uh, has if some if decision problem is a yes instance, if someone gives you a solution and or the proof that this decision problem is a yes instance, then if the problem lies in NP, then you can actually compress that proof to polynomial size, and then what you can later on do is you can hand over this proof to a third person also, and that third person can check in polynomial time whether uh, this is indeed the case, whether the given input instance is actually uh, solvable in polynomial time. So uh, think of these proofs as like objects which you have. So let's say there is an oracle or someone who solves this problem for you, and then the oracle, instead of giving you the whole proof, because maybe that's too, like if the oracle solves everything and says for some problem that the answer is yes, uh, and then that oracle gives you the whole proof, uh, then what you can do is you can take that proof, and now to make a third party believe that this indeed is the case, that this problem is indeed a yes instance. What you can do is you can just hand over this proof to that third party and some kind of a uh, polynomial time algorithm to a third party, and then the third party can verify by themselves that this indeed was the case, that the input instance was indeed a yes instance. So the third party won't have to solve the problem from scratch, which may take like large amount of time or may not be possible at all. But if someone has solved it, after that, you can carry on the proof in your pocket because it's a small size. So yeah, and yeah, some of the most interesting problems, uh, s- uh, yeah, lie in this NP complexity class. For example, satisfiability problem, it has been studied for decades. There have been so many improvements, and still a lot of research is going on to improve the efficiency of satisfiability problem. And similarly, another problem is like longest path problem. So these kinds of problems occur a lot in like day-to-day instances, and people want to optimize these problems. And nowadays, people are since these problems lie in class NP, and we right now don't have any polynomial time algorithm to solve these problems. What people usually do right now, a lot of research is going into finding good heuristics for solving these problems, or maybe solving these problems approximately using neural networks or something. So yeah, but yeah, these are some of the hottest problems, and have been like very sought after problems for like I would say the past 50, 60 years. So, yeah. So for example, this why satisfiability problem in class NP. This is because the proof of the yes instance can be just as satisfying as that. So suppose someone tells you that the satisfiability problem, given an instance of the satisfiability problem, it's a yes instance. How do you prove that this is a yes instance efficiently? Well, then it's just very easy. You just give the assignment at which this satisfiability problem uh, gives us the yes instance, gives us the yes output. So yeah, so or gives us the satisfying output. So yeah. And similarly, for the longest path, the proof of the yes instance that there indeed exists a path which occupies at least k edges is maybe just give us a path which actually contains at least k edges. That acts as a proof for the problem, right? And this proof is also called, usually in complexity theory, it's generally called like a certificate. And the polynomial time algorithm for verifying the certificate is called a verifier. So given any problem in NP, you can have a small certificate for that problem. If the problem has a if the problem is a yes instance, then you can have a small certificate for that, and that certificate can be verified by any party in polynomial time. And similarly, now what's the problem? What's the complexity class co-NP? So co-NP is the set of decision problems for which. So right now we define NP. In NP, we said that the complexity in the NP complexity class, every yes instance has a certificate, has a small certificate and an efficient verifier. Similarly, what's the complexity class co-NP? Here, every no instance will have a small certificate, a polynomial. By small, I mean polynomial time, polynomial size, and uh, efficient verifier, I mean that the verifier verifies in polynomial time. So right now, like we are not into this fine-grained thing where n cube or n square matters to us. What matters to us is whether something can be exponential or polynomial. Like something can be done in polynomial time or it requires more than polynomial time. Not exponential, but yeah, more than polynomial. So yeah. So for example, what's an example of a co-NP problem? So the unsatisfiability problem. So unsatisfiability problem asks, uh, given a given a Boolean formula, does there exist any assignment at which or the unsatisfiability problem actually asks that given a Boolean formula, for all variable assignments, is this formula false? If it is true, then actually that formula is unsatisfiable, and so it's a yes instance. So a yes instance in unsatisfiability problem is actually a no instance in the satisfiability problem. So similarly, a yes instance in the satisfiability problem is a no instance in the unsatisfiability problem. So how can you have a small certificate for the unsatisfiability problem? Uh, you just take, so you want a certificate for every no instance. So what maybe a certificate for a yes instance, which is just maybe a Boolean assignment of Boolean variables at which the formula is actually satisfied. So if you find some assignment of Boolean variables such that the formula becomes satisfiable, then you know that this is a no instance for the unsatisfiability problem. And that's why there exists a polynomial size certificate for the unsatisfiability problem. So yeah, what I just described maybe like saying that every yes instance of satisfiability problem is a no instance of unsatisfiability problem and so on. So this can be described a bit more formally. Uh, so suppose sigma star is a set of all strings over sigma of finite length. Uh, then maybe like why did we move on from like yeah these problems to these strings? Because like every problem can be encoded as a string. Like every instance of a problem, input instance of a problem, can be encoded as a string of finite length over some alphabet sigma. And now hmm, yeah, so yeah, the pro so suppose for so like the set of all strings denote maybe all the instances for a given problem, and from that only like some of them are yes instances and other instances are no instances. So let's suppose that the set of strings L corresponds to the yes instances. So L bar corresponds to the actually no instances. So an instance is a string with the alphabet alpha. Of course, every string needs to not be a valid instance. So L L belongs to NP if and only if uh, yeah sigma star minus L belongs to co-NP. So yeah. Uh, so this is because like what I just described that uh so if they so L belongs to NP, essentially this means that there exists a, uh small certificate and a efficient verifier for the yes instances. This will be true if and only if for the complementary problem, which will the problem of sigma star minus L. Uh, so sigma star minus L will be the problem which has yes instances for everything apart from sigma star minus L. Like apart from L, for every other string, if it's a yes instance, then it's the complementary problem of the original problem. And so essentially we say that L is in NP if and only if sigma star minus L is in co-NP. And that's why the same certificate and the same verifier for L continue to work for the problem tau as well, which is the complementary problem of L. So as I just described, this satisfiability and unsatisfiability are complementary problems because yeah. the set of yes instances for SAT are precisely the set of no instances for unsat. And that's why the same certificate and the same verifier works for both of these. So yeah. So yeah, one can just explain this maybe a bit more formally that yeah. Uh, so the problem L lies in NP if and only if the problem tau actually lies in co-NP. And what is tau? This is just L bar. So like sigma star minus L is the so yeah. And now hmm, what's observation? So yeah, this was discussed in the lectures as well that essentially uh, P is a subset of NP and P is also a subset of co-NP. So what do we mean by this? So essentially what this means is that yeah, the problem P like uh, so any problem which can be solved in polynomial time also lies in the class NP. And similarly, any problem and so also any problem which can solve in polynomial time also can also lies in the class co-NP. So any decision problem, yeah. And uh, uh, just a minute, guys. Maybe I'll just mute myself for a second. Yeah. So the language L lies. So we're discussing that the language L lies in class NP. Or the set of strings lies L lies in the class NP if and only if the set of strings like the complementary set of strings like sigma star minus L lies in the class co-NP. And now moving on, we are saying that any problem which lies in the class P. The class P is essentially a problem which has a polynomial time solver. So that problem also lies in the class NP as well as the class co-NP. So what this means is that any problem which has a polynomial time solver also has a compact certificate and an efficient verifier for every yes instance as well as for every no instance. And why is this true? So it's a very simple idea. The idea is that yeah. So you don't have any certificate, so just use no information as a certificate, like use empty string as a certificate, and the verifier is just your original polynomial time algorithm for the problem. And then this verifier can actually just output whether the instance is a yes instance or the instance is a no instance in polynomial time because the problem lies in the class P. So that's why yeah, a problem lies in So that's why if a problem lies in if the problem pi lies in a complexity class P, then it lies in NP as well as co-NP. So this is what so essentially from this Venn diagram actually you can see that this is what the landscape actually looks like. So like the set of problems P. So this P is essentially the set of problems which can be solved in polynomial time. And then what's NP? So this is the set of problems uh, which like which have a compact certificate and efficient verifier for every yes instance. Similarly, co-NP is the class which has the certificate and verifier for every no instance, and P lies in both of these classes. And it's an open problem actually. Like, so right now in this Venn diagram, you can actually see that these things are shown as non-overlapping, but actually it's an open problem whether P equals to co-NP. So yeah, it's also a very big open problem, whether NP equal to co-NP. Sorry. And similarly, these open problems are also there. So we also don't know whether P equals to NP or not. So we are showing this P as a subset of NP, but we really don't know. It might be that. So it's a like $1 million problem whether this P is actually a subset. So we know that at least it will be that P is not larger than NP. This we know, but we don't know whether P is exactly equal to NP or yeah, something like that. And similarly, we don't know whether P is exactly equal to co-NP or not. So yeah. And similarly, after this, there is some further landscape of problems. So a problem is NP hard. So NP hard is kind of the set of problems which, if you solve those decision problems, actually, you will be solving all of the problems. If you solve any of the NP hard problems, you will be able to solve all the problems in the class. So yeah. So what do I mean by this? So essentially, like, so there can be like, so NP hard is a set of problems. So suppose if you take any problem out of this, then if you are able to solve that decision problem, then actually you will be able to solve all of the decision problems in the class NP. So these are what are called NP hard problems. And similarly, what are co-NP hard problems? Co-NP hard problems will be some further set of problems which, if you solve any of those problems, you will be able to solve all the problems lying in the class co-NP. So a problem pi is called NP-hard if existence of a polynomial time algorithm for pi implies existence of a polynomial time algorithm for every problem in NP. Yeah, I was saying that you'll be able to solve the problem. What do you mean by solve the problem here? Because we are just looking for polynomial time stuff. So like essentially solving a problem means like solving that problem with polynomial time for now. So if you can solve any NP-hard problem in polynomial time, you will be doing humanity a great favor because you would have then solved every problem in NP in polynomial time. And now what are NP complete problems? So NP complete problems are really nice problems. Uh, so NP complete problems are essentially the hardest problems in the class NP. And why is this? So NP complete problems are the problems which belong to the class NP as well as the class NP hard. So problems, so there exist such problems actually. So one might wonder why is this even true? Like why does NP hard and NP need to have an intersection? Like why should there exist a problem? Like if there exists a problem on which solving it you can solve whole of NP, then maybe uh, that problem need not be an NP problem itself. But turns out it's a very beautiful result. Like it's what's called the Cook-Lewin theorem, or yeah, which started all of this complexity theory area of like P and P and everything. So essentially, yeah, there exist problems which are NP hard as well as lie in the class NP. And these problems are called NP complete problems. Essentially, you can think of them as the hardest problems of the class NP because solving any of the NP complete problems, which themselves are problems lying in NP, will give you polynomial time algorithms for every problem in the class NP. So yeah, so NP complete problem is the hardest problem. And now, whenever we are saying, okay, so till now we have been discussing, okay, like if you solve this problem, then you will be able to solve some other problem. What do we actually mean by this? Like solving a problem A implies solving a problem B. So this is where this concept of reduction comes into the picture. So reduction is a tool usually used to compare relative hardness of two problems, which essentially, so on a very high level, without going to definition, what it means is that, okay, if I give you a black box, or if I give you a machine, let's say, if I give you a machine which solves a problem B for you, you don't know how that machine works, you don't know the internal workings of that machine, but I just give you the machine, and that machine solves the problem B for you. Then can you use the problem? Then if you can use that machine to solve some other problem A for you, like suppose, so you can have a machine which solves some unrelated problem B for you, and then what happens is you use that machine to solve some other problem A for you in polynomial time. Then actually, or not in polynomial time, but yeah, like just use that machine as a black box to solve the problem A for you. Then you can actually say that the problem A reduces to problem B, because now if you really want to solve problem A, you really don't have to think about problem A at all. What you can focus on instead is just the problem B itself, because now you have established that okay, if I solve the problem B, then I can, like using the problem B solver as a black box, solve the problem A also. So that's why you can now, instead of focusing on problem A and B separately, you can just focus on problem B. And this is kind of a power of reduction. And if we are talking about this computational complexity or establishing NP hardness or something, so usually we are so here usually we are interested in polynomial time algorithms and everything. So essentially, what we in here is so what we'll be discussing here are maybe like a polynomial time reduction. So suppose if you are given a solver for some problem B in polynomial time, then can you solve the problem A in polynomial time as well? So we'll be mostly dealing with this thing, at least for the scope of this session. And here's where, like there are different kinds of reductions. Like these are mostly nomenclatures, but it's like since we are standing on the shoulder of giants, it's good to know like when these concepts came about, what were they called, and so on. So what's a Turing reduction? So we say that a problem A Turing reduces to another problem B if there exists an algorithm for problem A, which is allowed to make polynomially many oracle calls to an algorithm for problem B, and otherwise runs in polynomial time. So essentially, what's a Turing reduction? So what I just described to you was the Turing reduction. Essentially, if you're given a solver for problem B, which solves the problem B in polynomial time, then uh, uh, a Turing reduction of problem A to problem B will essentially be a reduction where you make polynomially many calls to problem B for solving problem A. And so essentially you have solved problem A in polynomial time as well. If you have solved polynomial B, problem B in polynomial time. And maybe there might be some other computation involved also, and it should also for solving problem A. And that side other computation should also run in polynomial time. So yeah. So this is what is called Turing reduction. And there is yeah, there is that actually, like there's not a result, like it's very easy to see that satisfiability Turing reduces to actually unsatisfiability. So yeah, if you have a polynomial time solver for satisfiability, then actually you have a polynomial time solver for unsatisfiability also, because checking if a problem is satisfiable or not in polynomial time essentially means you have also found out whether the problem is unsatisfiable in polynomial time. So yeah, so yeah, and yeah, I think this is just saying the same thing. And usually, how do we denote these things? Suppose there are two problems, pi 1 and pi 2. So if pi 1 Turing reduces to pi 2, then we write pi 1 is like this kind of a notation, pi 1 less than equal to like Turing pi 2. So essentially here, okay, if so essentially, what's the harder problem now? Like if pi 1 Turing reduces to pi 2, it means that if we have solved the problem pi 2, problem pi 1 will automatically be solved. So a lot of people get confused in this notation. So please, like, I would advise you to uh, read it and listen to it very carefully. That uh, if problem pi 1 reduces to problem pi 2, then problem pi 2 is the harder problem. Why is this the case? Because if you have solved for pi 2, then pi 1 is solved automatically for you. And what this means is that pi 2 was actually a harder problem, and that's why you were able to solve problem pi 1 as well. And that's why we write this in this kind of a notation, that pi 1 less than equal to pi 2. And essentially what this so this kind of a less than equal to symbol also kind of denotes the hardness. Like pi 2 is a strictly harder problem than pi, or not a strictly harder, but like pi 2 is at least as hard as pi 1. Yeah, in terms of like polynomial time computation. So yeah. And similarly, what's a car reduction? So car reduction and turing reduction are really like two faces of the same coin, I would say, like just saying a bit things a bit differently. So a problem pi 1 car reduces in polynomial time to another problem pi 2 if there is a polynomial time algorithm A which takes an instance of pi 1 as input and outputs an equivalent instance of the problem pi 2. So essentially, in Turing reduction, what we were doing was we were we were trying to use the solver of problem, let's say pi 2, to solve the problem pi 1. But now in calculation, what we say is okay, we are not doing polynomially many calls to the solver of problem pi 2, but instead now what we are saying is like actually problem pi 1 and pi 2 are completely identical. And what this means is that like uh, every instance of the problem pi 1 can be converted to an equivalent instance of the problem pi 2. So yeah, essentially like a problem pi 1 car reduces to problem pi 2 if and only if there is some mapping of, let's say, A such that like any instance x of the problem pi 1 is a yes instance of is a yes instance if and only if A of x is a yes instance of problem pi 2. So there is a one-to-one mapping between the yes instances as well as the no instances of the problems pi 1 and pi 2. So yeah, and this is what is called car production. So essentially, like again, it's the same thing. Like if a problem pi 1 polynomial time car reduces to another problem pi 2, then if there exists a polynomial time algorithm for pi 2, then there is a polynomial time algorithm for pi 1 as well. So yeah, and similarly here, like one can write. So if like essentially solving the problem pi 2 in polynomial time will give you a solver for pi 1 in polynomial time as well here also. So that's why pi 2 is strictly harder in terms of car. Not strictly, but pi 2 is as hard as pi 1. And that's why we denote it as pi 1 is less than equal to pi 2. So yeah. And there's a very like, simple observation which one can make like that the complexity classes NP and co-NP are actually closed under polynomial time car reductions. So what this means is that if a problem lies in the complexity class NP, then uh, if there is a car reduction of like pi 1 to the problem pi 2, then it means that the problem pi 2 should also lie in the class NP. So something like that. Yeah. And now, yeah, now comes the so right now we were just establishing some things, and now why we are actually like studying this as an area. Like, how did this area actually develop? It is because of this beautiful result by Cook-Levin. So this is called Cook-Levin theorem, which says that satisfiability is NP complete. So remember that we like I raised you the question like why does such a problem even have to exist, which lies in the class NP as well as is NP hard. So actually satisfiability is such a problem. So we know that satisfiability lies in NP, but Cook-Levin theorem also showed that this problem is NP hard as well. So essentially solving the satisfiability, if you solve this problem satisfiability, then you will solve all the problems in the class NP in polynomial time. So yeah. And yeah, and after that we discussed some in the lectures there were discussions around using this very big hammer to settle the complexity landscape for some other problems as well. So for example, just a minute. Yeah, sorry for that. So then there it was discussed in the lectures how can one obtain uh, uh, how it was in the lectures that if SAT is NP complete, actually one can show that CNF SAT is also NP complete. So essentially, which means that yeah, that SAT reduces to CNF SAT. So yeah, there was reduction shown in the lectures also that actually SAT reduces to CNF SAT, which means that if you solve CNF SAT in polynomial time, then you can solve SAT in polynomial time as well. But note that CNF SAT is in itself a NP problem. So what this means is that CNF SAT is also NP hard as well. And that's why CNF SAT is also NP complete. Yeah. And then one can also show that yeah, there are three SAT, which is three CNF SAT, where like every clause in the CNF SAT is of size 3 is actually also NP complete. Yeah, one can reduce three CNF SAT to again CNF SAT and show this. But note that one very interesting thing to note here is that actually two CNF SAT like is a problem solver in polynomial time, which we discussed last time when we were uh, which was discussed last time when there were discussions about Markov chain. Like there was an algorithm which actually was Markov chain based algorithm which was solving two CNF SAT in polynomial time. But as soon as you increase the size from 2 to 3, then 3 CNF SAT actually becomes an NP complete problem. And then yeah, in the lectures there were discussions around some NP complete reductions. For example, for the problem of independent set, first of all, what is this problem? So suppose you're given a graph. So all of these problems are actually really important graph problems in the practical world. And turns out all of these are indeed very intimately related to very unrelated problems of SAT and everything. So that's why this whole concept of like NP completeness, NP hardness, and these complexity classes ties up all the areas of computer science very beautifully. So indeed, that's why this Levin theorem is one of the most foundational results of yeah, at least computer theoretical computer science. So what's the independent set problem? So suppose you are given a graph G and an integer K, then one has to output whether there exists an independent set of size K or not. And what's an independent set? So in a graph G, a subset of vertices, a subset W of vertices is called an independent set if for any pair of vertices in the set W, uh, uh, there should not exist an edge between those pairs. So essentially, independent set is a set of vertices such that no two vertices of that set share an edge. So there does not exist any edge between any two vertices of G, any two vertices of W. It should be W, not G. So, for example, in this graph, so if this is the graph, then uh, uh, the set of vertices A, E, F. So this A, E, and F. You can see that there is no edge between any pair of vertices from this set A, E, F. That's why A, E, F form an independent set. Similarly, the set A and D form an independent set. But A, D, F is not an independent set because now D and F are sharing an edge. So yeah. And then it was discussed in the lecture, like it's a really nice reduction, which shows that the independent set problem is NP complete. Uh, and this is by showing that actually 3-SAT reduces to independent set. Essentially, if you have a polynomial time solver for independent set problem, then you can solve the 3-SAT problem in polynomial time as well. So, yeah, and yeah, for this, there was some reduction using uh, taking a triangle for every clause and everything. But yeah, you can go through that reduction uh, and see it again in the lectures. I'm not discussing the reduction here. And usually, how do these car reductions look like? So yeah, so essentially in car productions, as we already discussed, that to say that a problem pi 1 car reduces to problem pi 2, you have to indeed obtain some mapping from between the instances of pi 1 and instances of pi 2. Essentially, uh, for any from any arbitrary instance x of pi 1, you have to construct some instance y of pi 2 in polynomial time, such that x and y are equivalent, in the sense that x is a yes instance of pi 1 should imply that y is a yes instance of pi 2, and x is a no instance of pi 1 should imply phi is a no instance of pi 2. So this is the outline of car productions, and this was uh, used for independent set. And then there was the second problem which was discussed, which is, I believe, the problem is this is vertex over. Yeah. So what's the vertex over problem? So a graph, given a graph G and an integer k, suppose the graph is undirected and unweighted. Does there exist a vertex over W of G such that size of the set of vertices, like the number of vertices in that vertex cover is less than equal to k? And what is a vertex cover? A set W of vertices is called a vertex cover for the graph if for every edge of the graph at least one of its endpoints belongs to W. So essentially, like uh, every edge should be covered by a set of vertices. Like at least so every edge should be covered by at least one vertex of the set W. This is what is called like the vertex cover. Yeah. And what do we mean by covering an edge? Essentially, at least one endpoint of the edge should lie in the set W, and that's when we say that that edge is covered. And so, if all edges are covered, then the vertex W is called a vertex cover. So, for example, in this graph, uh, like the set, let's say if you have to cover all these edges, if you just take, let's say, the vertices, so one very trivial vertex cover is just the whole set of vertices. So if you consider the whole graph, the set of vertices A, B, E, F, D, C, then this is indeed a vertex cover. But now we have to answer actually the minimum possible size set, because we want to check for a given k whether W is less than equal to k. Size of W is less than equal to k. So another possible vertex cover here may be like considering the set of vertices A, B, and D. But if you consider the set of vertices A, B, and D, still like this edge won't be covered. So you need to take one of E and F also. So maybe A, B, E, D is one of the vertex covers. Yeah. And but you can actually remove the vertex B from the set also. So this ADE is also a vertex cover for this graph, because every edge has at least one endpoint in this set ADE. So yeah. And then actually uh, there was this reduction also which was discussed, that vertex cover problem is also NP complete. And this was shown by showing that the independent set problem which we just discussed actually reduces to the vertex cover problem. So given a polynomial time solver for vertex cover problem, one can solve the problem of independent set also. Yeah, it's not too hard to see why, but yeah, you can go through that in the lecture. And then one can introduce some other problems as well. So another problem which was discussed was the click problem. So what's the click problem? So given a graph G and integer k, does there exist a click of size at least k in the graph G? And what's a click? So a click is a subset of vertices W such that we have an edge between every pair of vertices. So in independent set, we said that there should not be an edge between any pair of vertices. But in a click, it's the opposite. A click is a set of vertices such that every pair of vertices between that set should have an edge. So for example, in this graph, maybe like this set E and G. So if we just take two vertices, then if there exists an edge between those two vertices, then it forms a click. So this E and G is a click. Similarly, every singleton vertex is a click. So A is a click, B is a click. But if you're looking for like larger size clicks, then there's a click of size 4 here, like A, B, C, D is a click here. Because in the set A, B, C, D, if you take any pair of vertices, let's say A and D also, there exists an edge, C and P there exists an edge, and so on. So yeah. So click is a subset of vertices such that we have an edge between every pair of vertices. And for example, in this graph, this is an example of a click. And then, yeah, the reduction was shown. This was shown using again independent set that the click problem is NP complete. Essentially, one can show this by reducing again the independent set problem to the click problem. So yeah, this was also discussed in the lecture. So essentially, if you have a and note that why are we saying NP complete, not just NP hard? So by showing reduction, let's say by showing a reduction that if you have a polynomial time solver for click, you have a polynomial time solver for independent set. But that only shows that the click problem is NP hard because solving a click problem in polytime solves the entire class NP in polytime. But you also have to show that this click problem lies in the class NP itself for it to be NP complete. So for a problem to be NP complete, it has to be NP hard as well as it should also lie in the class NP by itself. And yeah, one can actually show that this click problem also lies in NP. And why is this the case? Because again, what's the certificate for this problem? A small certificate for the problem. Just the click itself is a certificate for a yes instance. So if there's a yes instance, then there exists a small certificate which is the click itself, and it can be verified easily whether the given certificate is indeed a click or not. So yeah. So note that like this is also one very important thing which people tend to like ignore sometimes. That for showing NP completeness of a problem, you just don't need to show the appropriate reduction. Like reduction just gives you the NP hardness part. You also have to show that the problem actually lies in the class NP itself. Because if the problem itself is not NP, then it might just be NP hard, but it might not be NP complete. But for showing NP complete, you have to show it is NP hard as well as it lies in the class NP. Yeah. So the click problem in itself is actually NP complete. So I guess this was all the theory which I had actually uh, prepared, like which was discussed in this week's lectures. So yeah, not a lot of very complicated stuff, but more of a introduction to like complexity theory and everything. So yeah. So since like if there would have been some people in present in person in the session, then I would have loved to take some doubts. But I guess since there is no one present in person in the session, maybe we can just move on to straight to the question. I haven't prepared a lot of questions because this week most of the most of the things were theory. So preparing these theoretical questions like in an objective manner is like not really the easiest thing. And yeah, it's and anyways, like this week was a bit more on the lighter side because it was more of an introductory. Uh, these were introductory lectures, so yeah. So the problems shouldn't be too difficult either. But yeah, let's just discuss them nonetheless. So suppose so the first problem says that so if a decision problem can be solved in time, like let's say order of n to the 100, where n is the input size. So given an input of size n, if a decision problem can solve n to the 100 time, then the problem is in NP. Is this true or false? So usually in polynomial time, we would like to have like n square, n cube, these kinds of algorithms which have like a small exponents in uh, of n. But here, like even though like it takes like a very large, like sometimes maybe it would be faster, like for some instances to have a 2 to the n time algorithm rather than an n to the 100 time algorithm. But for theoretical purposes, actually, yeah, this n to the 100 also qualifies as a polynomial time algorithm because n to the 100 is a polynomial, right? So yeah, in a practical setting, one might for small values of n, one might even look forward to a like a 2 to the n time algorithm instead of n to the 100 time algorithm. But yeah, if n goes to infinity, like in asymptotic behavior, this is definitely much faster than 2 to the n time algorithm or something. But yeah, just okay. So since n to the 100 of polynomials in n, hence the problem is the class P, is in the complexity class P. Okay, class P, hence the statement is true. So yeah, let's say we move on to the second question then. So the second question says that if the fastest known algorithm for a decision problem runs in time n to the log n, where n is the input size, then the problem is known to be in P. True or false? So yeah, essentially one can see that yeah. So how do we define polynomials? So polynomials are essentially a polynomial is n essentially uh, like in a polynomial the powers of n should be just like even though these constants can be very large, the powers of n can be very large, but they should be finite constants. The powers of n should be finite constants. Whereas here actually this is not a polynomial because n to the log n, like this log n is not a finite constant because as n tends to infinity, log n also tends to infinity. So yeah, so n to the log n is actually not polynomial time. So if n to the log n is not polynomial time, then one might say that the problem is not in P. But note the wording, like one thing why I had this question was just please carefully look at the wording of this problem, like why I worded the problem this way. So how I worded the problem is if the fastest known algorithm, so known is the keyword here. So this is a very important keyword. If the fastest known algorithm runs in time into the log n, then the problem is known to be in P, true or false. So, like, why am I stressing on these words known? So it might be that, so similarly for these NP hat problems also, it might be that these problems really are solvable in polynomial time. Like, but we have just not been able to find such an algorithm for these problems, which is the like uh, $1 million P equals to NP question. But yeah, so similarly, like it might be possible that the problem which you are describing, the fastest known algorithm runs in time into the log n, but there might exist some uh, polynomial time algorithm for the problem, but we have just not yet discovered it. That's why the fastest known algorithm runs in into the log n, and that's why one cannot just rule out that this problem is not in P. One can just say that this problem is not known to be in P. So one needs to carefully look at the wording here. Like it's so if you have a like exponential time algorithm for a problem, it does not mean that the problem is not in P. It just means that the problem is not known to be in P. Because it might be true that the problem actually runs in polynomial time. It's just that we haven't been able to find out the polynomial time solution. So yeah. So this is I think very important to remember for everyone. Like this is one of the complexity theory or like theoretical CS 101. So yeah. So yeah. False uh, as into the login. Sorry. Into the login is not a polynomial in it. And why is this? Because uh, in polynomial, the degrees should be finite constants. So yeah, yeah. So this is not a finite constant. This is not bounded by a. This is not bounded by any finite constant either. Whatever like number you give me into 1000 into 10,000, I can always give you a value of n, at which n to the log n becomes greater than n to the whatever constant you give. So yeah, so that's why this is false. So then moving over to the third question. Third question is really nice. So if the if the fastest known algorithm for a decision problem runs in time, let's say 10 to the log n, where n is the input size, then the problem is known to be in P. So is this true or false? So if the fastest known algorithm runs in like time 10 to the log n, then the problem is known to be in P. Is this thing true or false? So one might be led to believe, okay, like since n to the log n also was uh, like not in P, one might be led to believe, okay, this also might not be in P. But actually, this is just a simple mathematical manipulation. Actually, like 10 to the log n can also be written as and like so this is property of like logs and exponents, right? Like this 10 and this n can actually be exchanged with each other. So actually, since 10 to the log n is actually equal to, so this is equivalent to saying this thing like 10 to the log n is actually equal to this n to the log 10. So these bases and these values inside the logs can be interchanged. This is a property of logarithms and exponents. So yeah, this is basic high school math. Uh, and then now one can say that yeah, if this is n to the log 10, this is bounded by, let's say if we are taking log with respect to, let's say, even base 2. This is like at most n to the 4. And n to the log 10 is bounded by n to the 4, uh, which is a polynomial in n, which is a polynomial in n. Hence, so what this means is that so this value, so this runtime is bounded by a polynomial in n, and this means that the problem is actually in P. So yes. And here you can even remove the known because like it's known to be in P. Like so it if it is known in to be in P, then it is actually in P. Yeah. Yeah. But if a problem is not known to be in P, it does not mean that the problem is actually not in P. It might be the case that the problem is actually in P, but we just haven't found us humans have not found a solution to that. So so yeah. and the problem is known to be in P. And state the statement as in the question is true. So yeah, so this is true, right? Okay, now comes another fun question. Like this is the last question for the day, but yeah, I find it a bit fun. So yeah, so you might have discussed or seen all these Dijkstra algorithm, Bellman-Ford algorithm for like shortest paths in a graph, right? So now what we are asking is, uh, the shortest path problem in a graph is NP complete. So is this true or false? So one might, okay, so NP complete is okay, is not, or yeah, okay, let's just keep it this way. So on first try, when on like if one just starts to think about this as like um, without much thought, one might go to the argument that oh, like shortest path problem, negative edge weights. We know that Dijkstra works on positive edge weights only, but if we have negative edge weights, then one can uh, use the Bellman-Ford algorithm to find the shortest path. So it might be possible that the shortest path problem in a graph with negative edge weights, like this is solvable in polynomial time using Bellman-Ford algorithm. But if the problem is solvable in polynomial time, then the problem lies in P. And like, yeah, we don't currently know that whether P is equal to NP or not. This is a very big open question. So this statement should be false. Like, if it was true that the shortest path problem is like NP complete, then we also have a polynomial time algorithm for this, which is the Bellman-Ford algorithm. So then one has just shown that NP is equal to P. Where's the fault in this? So actually, so the really interesting thing is like uh, Bellman-Ford and every like Bellman-Ford, Dijkstra, all the shortest path algorithms actually assume that. So like this statement, like one might think that this statement is false, but actually this statement is true, and I'll just tell you why this is the case. That actually shortest path problem in a graph is NP complete. So maybe just a caveat uh, that yeah, okay, it might be mm, confusing since there exist algorithms like Bellman-Ford find shortest path in a graph with negative edge weights, and hence shortest path problem should lie in the complexity class P. Uh, should be known to lie in the complexity class P. But what one should note here is yeah, and yeah. Uh, but one very important caveat is that uh, uh, the caveat here is that actually all these shortest path algorithms like Bellman-Ford and all these algorithms assume that the graph does not contain any negative weight cycle, right? So that's the caveat. So uh, yeah. So I'll come to why is this okay, maybe okay. Maybe we might be we might come back we can come back to this argument later. Let's just see why is this true? Like why is this problem incomplete with negative edge weight? So this is because uh, so we already know that the longest path problem. Uh, okay, it might not have been discussed in the lectures, but yeah, finding the longest path between a pair of vertices in a graph is an NP-complete problem. So finding the longest path in a graph is an NP-complete problem. And uh, if if you just negate the edge weight, so find the longest path is an NP-complete problem. But if you have a polynomial time algorithm for finding shortest path in negative edge weights, then what one can do is to solve this longest path problem, one can just negate its edge weights. Because now if every edge now has a weight of minus w instead of a original weight of w, then what's going to happen is the path which are longest earlier, let's say which had a like length of 10, will now have a length of minus 10. And so negating every edge weight makes the problem go from finding the longest path to finding the shortest path. Uh, and so like if you have a polynomial time algorithm which solves the shortest path problem in polynomial time, then you would have solved the longest path problem also in polynomial time. But that problem is NP hard, so we don't know as of yet whether it can be solved in polynomial time or not. And the longest path problem can be reduced to the shortest path problem by just negating the edge weights. So yeah, so if you can solve the shortest path problem in negative edge weights, then you would effectively solve the longest path problem also. But that's an NP complete problem. And so shortest path problem is also NP complete. And how do we show NP completeness? So this argument just gives NP hardness. But it can also be proven that this problem lies in NP because one can just give the graph itself. One can for like one for a verifier to verify whether there exists a path of like let's say length less than equal to k. The verifier just needs to give the certificate. You just needs to get the certificate of the path itself. Like one, you can just have the certificate as the path itself, which is the shortest, and using that certificate, you'll be able to solve the problem. So yeah. So the shortest path problem is also NP complete. And so like what I was discussing was okay, now it might be a bit perplexing to you that shortest path problem is NP complete. Uh, this can be added as a note, I think. Yeah. Like we know that in negative edge weights, but we know like how to find shortest paths using Bellman-Ford algorithm. So it should be known in the complexity class B, which should, which means uh, P equals to NP, and this is a very big like exclamation and question mark. Uh, but note that this is like life is not so easy. Like it's not true. Caveat here is that uh, mhm, uh, Bellman-Ford and other like Bellman-Ford and other polytime shortest path algorithms assume that the graph does not contain any negative weight cycles. So if the graph indeed contains some negative weight cycles, then actually these Bellman-Ford and all other algorithms will not be able to find the shortest path. Yeah. And here, whenever we are talking about shortest path, and whenever we talk about the longest path, we are talking about longest and shortest simple paths, where no vertices are repeated in the path. So yeah, I hope that's clear from the lectures itself. So yeah, yeah, yeah. But in the reduction we described above, so polynomial time algorithm or shortest path are only known when there are no negative weight cycles. Correct. And if there are negative weight cycles, then actually the problem is NP hard because uh, note that in the longest path problem also like if you are just negating the edge weights, then it might be possible that some cycles do become of negative weight because now you are assigning like any cycle which was a positive weight before will now be a negative weight cycle. So that's why yeah, in this reduction like you can obtain negative weight cycle, and so Bellman-Ford and all other tricks will not work. So yeah, so this is like pretty uh, interesting, and I think like one should really pay a lot of attention to uh, this kind of one should really pay attention to this kind of argument. Like yeah, that in general, like status path algorithm actually NP hard. It's just this assumption of like uh, having no negative weight cycles, which makes the problem easy for us. So yeah. So yeah. Okay then. So this is all I had to discuss for today from my end. So essentially, what we discussed was we introduced these notions of like NP complexity classes, P and what are ONP, and we saw some reductions, what are Karp reductions, Turing reductions, and so on. And then we discussed some like basic problems like uh, for based on these concepts. So which should probably help you out in your quizzes also. So I guess since there is a lot of time left, but there is no one present in the session actually, maybe I'll just wait for like maybe I'll just mute myself and wait for maybe 5-10 minutes. If someone like joins the session maybe in the last like half an hour to clear some doubts or something, so I'll be able to clear the doubts. So maybe I'll just mute myself for like 5-10 minutes and wait if someone joins the session to clear some doubts. So I'll just mute myself till then, guys. And if no one comes in the like let's say next 10 minutes, I'll just close the session. Okay, so I guess since no one has joined the session for any doubts, I guess I'll just close the session then. So thanks a lot for thanks a lot to everyone who's watching on YouTube. So hopefully I'll see some of you guys in person next time. So yeah, goodbye till then. Thanks a lot for watching, guys.